Okay, we're back for some more problems in physics problem solving with forces this time. We want to do some problems involving friction so we can understand how problems get solved when we don't know things like the coefficient of friction and how we can use forces to find those coefficients. So let's do the following example. Okay, we've all kind of experienced this. We've moved into apartments and we've had to move boxes and we've pushed them across the floor and felt the resistance of the box as it slides across the floor. So let's imagine I have a 32 kilogram box. In my case, this is a box of Lego bricks. I know 32 kilograms is a very small amount of Legos for me, but you'll have to deal with these unrealistic physics type problems. And suppose I'm pushing it across the floor at a constant speed of 0.5 meters per second. I'm pushing downward on the box as I'm pushing it with a constant force at an angle of 21 degrees and a total magnitude of the force that is 200 newtons. And the two things that I'd like to know are what are the normal force and what is the coefficient of friction between the box and the floor. Now, this problem I'm kind of pushing you, guiding you, by telling you to find the normal force first. Very often you'll get problems where you're asked to just find the coefficient of friction, and you can't find the coefficient of friction without actually looking for the normal force first. It's just in this case I'm guiding you. The other thing that you should note in this problem is that you're told some information that looks extraneous. And in this case, I've told you the value for the constant speed that the box is moving with. Now, the fact that the speed has a value of 0.5 meters per second is the extraneous bit. But the important bit, as we will see, is that the box is moving with constant speed. And that will be important to us when we apply Newton's second law to solve this problem. Okay, so let's go ahead and solve this problem. As with all problems, the place we start in forces is drawing a free body diagram. So I am pushing a box across the floor, and so the very first force I always put on is the weight because I know it's there. So there is the weight of the earth pulling on the box towards the ground. The floor is pushing up against the box, so that is the normal force of the floor on the box. I am pushing down on the box and diagonally, so this is the force that you exert on the box, and we were told that that's at an angle of 21 degrees to the horizontal. So I'm going to mark that on here so I don't forget, because I tend to forget those things. And then I may or may not know I'm done at this point. Okay, now I know this problem's about friction, so I know friction has to be on here, but imagine you didn't know. Okay, the key to this problem is that the box is moving at a constant speed, and that means the acceleration on the box has to be 0. And if I just look at this free body diagram, I know that the forces don't sum to 0 right now. In particular, there is a net horizontal force pointing to the right. And so at this point, if I didn't know friction was in the problem, I better be darn suspicious that I'm missing a force pointing to the left because I need a force that balances all of this out. Well, that force is indeed friction. If the box is moving to the right, the frictional force opposes that motion. And so this is the friction of the floor on the box. Okay? So at this point, I may or may not be done, but in fact, I think I am done. I think I've accounted for all of the forces, and I can set about going ahead to solve this problem. Now, the way I'm going to solve this problem is the way we always solve these problems, is with Newton's second law. And so the way I like to do Newton's second law is I like to break it into the horizontal and vertical components. So let me mark my plus x and my plus y directions here next to my free body diagram. And before I start, let me write out the components of this force vector because it is not pointing along those x and y directions. So the force of u on the box in the x direction is equal to the magnitude of the force you're exerting, which we're told is 200 newtons, times the cosine of that 21 degrees. And if I work that out, I get 186.7 newtons is the horizontal component of the force that you're exerting. The force that you're exerting on the box in the y direction is again equal to the magnitude of the force that you're applying, in this case, times the sine of 21 degrees. And if I work that out, I get 71.7 newtons. And then because I'm going to numerically need it, I know that the weight, in this case, is the mass times the acceleration due to gravity. That's 32 kilograms times 9.80 meters per second squared. And if I work that out, that's 313.6 newtons. Okay, so I think that's everything that I'm going to need to solve this problem. So now I'm going to apply Newton's second law. And what Newton's second law says is that the sum of the forces in each of the directions, the x and the y, has to equal the magnitude of the acceleration in that direction, the component of the acceleration in that direction, times the mass. So the sum of the forces in the x direction is the mass times the acceleration in the x direction, but we said the box is moving with constant speed, so the acceleration is 0. And if I look at my free body diagram, there's only two forces pointing in the horizontal direction. That is the force that you exert on the box, the x component of that force, minus, the minus indicates it's pointing in the opposite direction, the friction that the floor exerts on the box. Now I'm going to write one more line here, namely that this is equal to the force you exert on the box in the x direction. And I'm going to replace friction with what we know the friction is equal to. It's equal to this number that we call the kinetic coefficient of friction. It's the kinetic coefficient, because the box is moving, times the magnitude of the normal force. Okay, and it's important to remember that this is the magnitude of the normal force. We're talking about the horizontal direction, which in this case is parallel to the surface, and the normal force points perpendicular to the surface. So it wouldn't make sense to talk about the normal vector. We're only talking about the magnitude. And as we've discussed, we know that the friction depends on the magnitude of the normal because the friction increases when we push two surfaces together with more force. Okay, so we'll come back to that equation in a minute. Let's write down similarly Newton's second law in the y direction. So the sum of the forces in the y direction is the mass times the acceleration in the y direction. Again, the system is not accelerating, it's moving with constant speed, so that's equal to 0. And so this is equal to the normal force that the floor exerts on the box minus the force that you exert on the box in the y direction minus the weight that the earth exerts on the box. And again, these minus signs indicate that these two vectors, these two vector components, are pointing in the opposite direction as that vector component. Okay, so those are my Newton's second laws. And at this point, this is a pretty straightforward problem. I can jump to using numbers. So let's use the y equation first. I can do a little algebra there and show that the normal force of the floor on the box is equal to the force that you exert on the box in the y direction plus the weight of the earth on the box. And if I numerically put those numbers in, that is 71.7 newtons plus 313.6 newtons, the values I computed above. And so I find that the magnitude of the normal force is 385 newtons. Okay, so now I can go to the x component. And if I go to the x component, I can write from the x equation that mu k, the kinetic coefficient of friction, times the normal force, okay, that's just my friction, is equal to the x component of the force that you exert on the box. And I knew that from just looking at my free body diagram, because those are the only two horizontal forces, and I know that I'm moving at constant speed. So it's good that it algebraically works out. Okay, so if I solve this equation for the kinetic coefficient of friction, I find that that is the force that you exert on the box in the x direction. That should have been a b up there, divided by the magnitude of the normal force. At this point, I know both of those numbers. That's 186.7 newtons divided by 385 newtons. And so the coefficient of friction in this case is 0.48. It's a dimensionless number, and all it does is characterize overall what the interaction between those two surfaces are. In this case, the box and the floor. Okay? So that's a very simple example of a friction problem. Good luck doing some on your own, and we'll talk again soon.